All right, so today we're in for a treat. We have Professor Nir Shavit of CSAIL. So this is the MIT's Computer Science and AI Lab. And he is also, more importantly for this episode, the founder of Neural Magic, which has a fantastic tagline on their website, LLMs on CPUs, period. And so another thing they mentioned on the website is that they use model sparsity to accelerate open source LLMs and bring operational simplicity to Gen AI deployments. And so with that introduction, welcome back to the Data Exchange Podcast, Nir.
Thank you, Ben.
All right, so let's start with the basics for our audience. So open source LLMs, I'm assuming you folks work with all the popular ones, Llama family, Mistral, Zephyr.
Yes, we are just moving to do Mistral. We have been doing the Llama family and the MPT family. Yeah.
And completely focused on LLMs, no multimodal yet?
Yes, that's correct.
And let's see, so the goal is to assume that someone has already fine-tuned or pre-trained the model and you focus completely on deployment or inference.
We are focused on inference. The process that we have is either we're working right now to have an upstream model that is sparse, but right now the techniques that we're offering are techniques that are applied during fine-tuning. So when someone is fine-tuning their model, part of the thing they will do is sparsify and quantize it, and we inject ourselves in that part of the process.
So in terms of fine-tuning, you operate as other teams do when they do fine-tuning, which is basically someone focuses on their fine-tuning data set, and then you folks take over from there.
Yes, so we give the people a set of tools that they can use while they are fine-tuning their model, so that they can essentially take the model and during the fine-tuning also sparsify and quantize it, right, to a degree where it is actually recovering accuracy, but also is sparse and quantized, so that essentially the model is both smaller and more efficient in terms of execution on CPUs.
But the workflow for the user is in many ways their main focus is their fine-tuning data set, right? So
that's correct. They are using their fine-tuning data set, exactly.
So most of the effort, so this is what I found when I use, for example, the AnyScale fine-tuning endpoint, is most of my effort is really in the fine-tuning data set.
Absolutely. I mean, that's the way it should be, right, in some sense. Yeah.
Yeah. So next question is, so you folks are very much focused on inference on CPUs. And,
yes.
And historically, that has been the focus of the company. So tell us, remind us again, Nir, so why focus on CPUs instead of what everyone else is doing, which is GPUs or ASIC hardware like TPUs, right?
Sure. I think there are two reasons for this. We've always thought that CPUs have a lot more memory, right? And so if you could solve the compute problem, right, the fact that you need more compute, right, then the CPU is a naturally good environment because it can hold very large models very easily. And this is true, has always been kind of true. You can hold a lot of models or a very large model in the CPU memory, not a problem, right? So that's one thing. And then the limitation, of course, of the CPU is that it has a lot less compute. And so what do you do with that? And our solution, right, is to sparsify the model. So that essentially, right, instead of having to, have more flops come from a specialized piece of hardware, your regular CPU can actually do the work of running the model at a reasonable speed. And then the thing that it opens up for you, right, is a myriad of things starting from, on your desktop or on your laptop, right? It enables you to run a model locally. So all the issues that you have with connecting to a cloud provider in order to run your model go away essentially if you're running on your laptop or desktop, right? And then in the cloud, right, is a similar kind of problem, right? I mean, to fit large models into memory, you have to use multiple GPUs. People, make big efforts now in quantization in order to reduce model size so that the models will fit on a single GPU, because it seems like for many people, right, fitting on a single GPU is like a basic criteria for being able to run. It's not that, of course, a lot of the providers know how to run multiple GPUs at inference time together, but it seems like people want to run on a single GPU if they can, right? So being able essentially to sparsify and quantize lets you do that. And specifically for us, right, a CPU in the cloud that can run something, a model on a single CPU is kind of an advantage relative to putting together multiple GPUs to run it.
So give us a sense, Nir, of, so for example, let's take Llama 70 billion. So
Right.
you folks can run this on what type of hardware?
So a typical piece of hardware would be like an AMD machine, for example. So you take your Genoa or Milan server, and it has an abundance of memory. It can easily fit, the model in there. Yeah.
And give us a sense of, so do I lose anything as far as accuracy, or? So what are the measurement, what are
so
the
if you
metrics that
you
you use?
perform so to be fair, we don't have yet accuracy results for 70 billion model, but for the 7 billion model, I think you can see in our blogs what we're saying. Let's step back a second. So everybody wants to make the model smaller, okay? That means that if I measure, the measure here would be, how many bits do I actually need per weight, right? Or per activation, okay? And quantizing is one way to reduce the number of bits, okay, without losing accuracy. Another approach is sparsification, where I just remove weights, right? And Neural Magic views these two as part of the same scheme. We do both, right? And so if you took a typical model and you quantized it to 4 bits, then you would lose, people know how to do this now without pretty much losing accuracy. And then when you go down to 2 bits, it becomes very complicated. There are still no good schemes for 2 bits, okay? So if you pushed yourself down to 4 bits from there on right now, there is no real good way to keep on going in bit reduction, okay? Sparsity is a complementary technique that you add on to your 4 bits or 8 bits to push further in the bit reduction, right? And so we recovered to 99% accuracy, right, on the downstream of the model, right, and for inference, right, and we do that, right, essentially, by a combination of sparsity and quantization. So if you will, it's where you'll get to if you want to do if you can do 2 bits, but you can't really do 2 bits very well right now. And the beautiful thing about sparsity is that this is not the end of it, right? Because as the model gets bigger, my ability to sparsify, right, to higher degrees grows. Okay, we know that from scaling laws. So essentially, right, the potential here, if you're doing quantization, okay, you do 4-bit, 2-bit, 1.5 bits, eventually it's over. You can't go down anymore, okay? Whereas if you're using a combination of sparsity and quantization, there is, at least we don't know right now what the limit is, right? And just to throw you into my favorite space, right, which was biology, right? In the brain, right, there are extreme levels of sparsity. Okay, I don't know if the brain quantizes, but it definitely does. It is sparse. Okay, so we don't really know to what extent you could get away with very high levels of sparsity and still be accurate. I think that we believe, right, that both for specialized fine-tuned data, right, and in the general case, that you can get to very high levels of sparsity. Yeah.
Nir, for people who don't follow this closely, a couple of questions. First, this combination of sparsity and quantization, are there theoretical results? So are there theorems showing that this works, or is this all empirical in terms of?
Yeah, right. So this is empirical. All of this work is really empirical. So the theoretical work is in stating the mathematics of what specific quantization or sparsification algorithm you are doing, right? But then a lot of the work that is being done here is essentially an approximation of a more accurate calculation that you could do in order to sparsify or quantize something. So we don't really have the computing resources to do the optimal thing. And so what we're doing is approximating, things. And so the results that you get, right, are specific to a specific network with a specific data set. And on that, you can show that you can get very high recovery and very, and very fast performance, right? But this is not as if we have a theorem that is going to work everywhere. That's not the case, at least not now. Yeah.
So how do you know that you went about the sparsification and quantization correctly? So what are the performance metrics?
So we use the same performance metrics that everybody uses. So essentially, whatever you use in your fine-tuning process, that's what you should be using. So whatever process you used for testing your recovery after you fine-tune an upstream model to your own, curating it on your own data set, okay, whatever you're using, use that, right? And we have some examples, right, published, and we have others that we have not published yet that are going to come out in the next weeks and months. But the general idea is this, that you do your fine tuning, and while you're doing it, you apply our techniques, and you end up with a model that then you run with deep sparse on a CPU, and you get performance.
But because Nir, when someone releases a new foundation model or a new LLM, what they normally do is they say, okay, so this is how our new LLM compares with previous LLMs, and these are the different benchmarks, whatever they are, right? So there are many benchmarks, and then they go about comparing themselves to the other LLMs on these benchmarks. So is that something that you folks do as well? So here's my sparsified whatever Llama 7 billion.
And I compare it to Llama on the benchmarks that Llama tests.
Yeah.
Yes. But what I'm saying is that, as people have found out, the fact that something fits a benchmark, that the perplexity is a certain perplexity, doesn't mean that I'm actually going to get results that are good enough for me, unfortunately, right? And so what we're kind of saying is that there is an additional test here that has to be done. When you're fine-tuning downstream, you should be using whatever criteria you use for your fine-tuning, and just make sure that your sparse fine-tuning gets to the same level as your fine-tuning. And that would be the ultimate measure, because that's really what you would have. Imagine you didn't sparsify, right? Then you have a certain accuracy and a certain type of behavior for your model that's what you're expecting, right? And that's what you're satisfied with. And so our goal would be to sparsify and quantize and get the same thing.
I see. And
I'm kind of saying general benchmarks are great when you want to, compare models and so on, but specifically for a customer, right? It's about their application, right? And so the ultimate measure is what I said. Yeah.
So I guess I got a little bit confused, because as you noted earlier, so this actually you guys come in the fine-tuning step.
Yes.
Right. So it's not like you're saying, we're going to take Llama 7 billion, sparsify it, and now we have a new version of Llama 7 billion.
So just to be fair, we are working on that.
Okay.
So we are working on that, but that is not the stuff that we are providing right now to customers. What we are providing right now is essentially sparsification during the fine-tuning step. So not the upstream. Yes.
So why would the fine-tuning Llama itself, so taking Llama 7 billion, the pre-trained model, and having a sparse Llama 7 billion, why would I use that over just fine-tuning Llama itself? I guess there are reasons why I might want to run Llama itself on a CPU. as opposed to fine-tuned Llama, right?
So the reason that you're sparsifying and quantizing is the same reason that everybody is busy with that, is that essentially if I have a smaller model, I can run it on more things. So if I want to fit my model onto a MacBook Air, then I need the smaller it is, the better it is for me. And so smaller is reduction in the number of bits per weight, right? And so what we're saying is, okay, we can get you down, right, by a very large factor through a combination of sparsity and quantization, right?
Yeah, and there are reasons why you might want to run the pre-trained model, right? So for whatever reason, for example, you might just be doing general summarization, but you want to do it on a smaller device, right? So,
right.
yeah.
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 So I'm kind of saying the reason to do this process, right? This is not about accuracy, right? This is about getting speed. And people are willing, as we see, to lose some accuracy for the purpose of actually fitting it on smaller devices or for getting speed. And so that's where we are coming in, to help speed up and make the model smaller. That's
And to what extent the things you've been discussing, to what extent I assume none of this is open source, right?
No, so all of this is open source.
Okay. Wow.
So all of our ML processes and everything are in the public domain. You go to SparseML and you can download them, and you can get the models from our library. So the SparseZoo library. So everything is open source. The thing that is not open source is our runtime. Right. So the runtime, which will let you run on a CPU fast, right, that is not open source.
Okay. So are you able to share some early use cases in customer success stories?
So we are still in the process of getting there. We don't have customer success stories yet. So in the sense that we have decided basically to move into this LLM space. This happened several months ago, right? And these are our first steps into this space. And hopefully we will have success stories very soon.
So you mentioned earlier that people are willing to sacrifice some accuracy.
Yes, this is with discussions with customers, but I don't have a result to describe to you yet.
Yeah. So what's your sense of how much accuracy are they willing to sacrifice?
Well, you should just look at you should look at things like Llama.cpp, for example, and what people are willing to do there. You should also look at when people are actually describing 2-bit quantization techniques, right? You can see that there's quite a bit of loss there, and still people are trying to run 2-bit quantization despite the loss, right? So this gives you a feeling of what's out there, right? So to cut the model size by a factor of 2, right? Using, well, it's not exactly 2, but but from going from 4 to 2 bits, people are willing to actually suffer a degradation, right? And so sparsity will get you there today without the degradation, right? So that's kind of
so once you sparsify the model, so what sorts of experiments have you folks done in terms of once a model is sparsified, let's see, so obviously it's much faster, it's cheaper to operate, but to what extent is it actually much faster than the non-sparsified model?
Right. So again, I think one has to think about this as a combination of sparsity and quantization. So if you think of a typical 4-bit quantization, it'll get you, I don't know, 3.5x reduction, right, in the relative number of bits per weight. Okay, and we push it more closer to the 2 bits, right? So you can get you know, I'm sorry, let me be accurate here. In terms of the bits, right, you are going with sparsity, right? If whatever, let's say 8-bit model you had, right? If I throw 50% sparsity on top of this, right, I'm essentially now cutting the representation by half, right? So that's how you should think about it, is what is the total bit reduction, okay? And so you get another additional total bit reduction, and this is, by the way, at 50%, you know, what we published is 60% recovering full accuracy, and today, not published yet, we can do between 70 and 75%. So it's about a 4x reduction in the you know, in the number of bits of the representation, right? And you know, and this should improve even more as you go higher up in the sparsity. Okay, so that's kind of where we're pushing. And then in terms of speed, I think if you looked at our blog, we're in the 6 to 8x speed up, and this is again relative to you just running at FP16 on your machine, right?
Which is incredible for user experience, right? So, because no
yes, I think so. Yes, exactly. So I think the thing, you know, if you're doing decode, right, and you're just waiting for things to happen, right, then I think people are willing, you know, to just it's a combination of speed and can I fit it. So once people have managed to fit the model on, right, then they start worrying about speed. And so we're kind of solving both problems, right? We're telling you, listen, you're both going to fit it onto your machine, and you're going to run really fast, as if you had a coprocessor on that thing.
Yeah. So in my mind, there's multiple reasons for wanting to use this kind of technology. One is obviously you have more hardware to use because there's actually more CPUs than GPUs. Secondly, you have more control, maybe, because specifically if you want to run the models locally, then you have more control. And obviously cost, right? So,
my view of the world, you know, might not be the standard view that you know, everybody seems to be placing, you know, the LLM in the cloud. So these are all LLMs out there in the cloud, and you know, and yes, people are trying to run it locally, but a lot of the stuff that's happening right now is essentially across the internet, right? But we already are seeing the problems that this kind of brings to the world, right? And you can do that. It's really good for certain things, right? But if everybody, for example, wanted to, you know, to run at the same time locally on there, you know, it would start to get really heavy, right? So offloading compute onto people's own devices is a very natural way to go about this, right? Or a combination thereof. Right?
Which is what happened in computer vision and speech.
That's right. For example, and so kind of this is kind of our view on this, right? That there is a big role for running on CPUs, and in addition to that, right, even in the enterprise, people still have enormous amounts of CPUs available to them that are essentially sitting idle, you know,
or the cloud providers even. Right?
Yes, even that, exactly. And so, you know, so those are resources that one can tap into if you could get reasonable performance, right? And that's what we're offering essentially.
So neural magic today, so you mentioned AMD, but does everything we've talked about also work for other CPUs, Intel,
yes, we run
Apple
on
CPU?
We run on AMD and Intel and ARM, all of them.
Okay.
Yeah. It's you know, there are differences in terms of the support for vector operations, which are the core of what you need in order to run fast, right? But all of these providers, right, actually do give you vector operations, and we are able to run on all of them. Yes.
So if you were to predict a year from now, what percentage of LLM inference will be running on CPUs versus GPUs?
I'm not going to get into that business.
Yeah, yeah,
But I will say, right, but you can see, right, that everyone is still, I mean, even though you have H100s and A100s, you don't see everybody running on an H100. It's not just because they're hard to get, right? It's also the expense, right? If I could run on a much cheaper device, right, or a device that I already have, then that would be a win, right? So people are still trying to run these models on T4s, right? I mean, it's not like now that, you know, and it's hard to run, right? It's hard to run a large LLM on a T4, but people want to try to do that. So they're really busy in in compression, right? And we offer sparsification as a way to do that, right? So it is really something that I think is going to be universal and is going to keep on happening. No matter what the high end looks like, there will always be a large fraction of things where people want to run them, you know, on less expensive devices or more easily available devices. That's where neural magic comes in.
So, Nir, for those of us who don't follow this closely, so can you place neural magic in the context of other efforts, like you mentioned, Llama.cpp? So, what are the other things happening in this kind of CPU inference space?
So, you know, I think if you look, you'll see that every inference runtime actually has a CPU version. It's not right. You know, it's like if you look at Onyx runtime, it's not that Onyx runtime offers a CPU runtime, and AMD have their own CPU runtime, right? And people have, you know, and there's Llama.cpp, and there are, you know, Facebook has said that they have their own CPU runtime. Everybody's got, you know, a solution here that runs on a CPU. And this is because we do want to run things on CPUs in the end, right? And so I think we just join the plethora of these solutions, but instead of just trying to do things, you know, make things smaller based on quantization, we're offering kind of, I would say, the future of where this can go. Because as I said, I think quantization has its limit. We are going to maybe push through 2 bits, but I don't think it's going to be easy to push beyond that. Meaning, let me say it in a different way, okay? It's not that you can't keep going down the bits. You can, right? It's just getting harder. The algorithms are getting more complicated, right? And so sparsity is offering you an easier path in some sense, right? That's the thing.
Yeah. And also, I think the other trend that will have an impact here is the fact that people are realizing that they will need, there's not going to be a monolithic LLM. They'll have multiple custom fine-tuned LLMs for each specific task.
Yeah, I mean, that's what it looks like. I mean, it's very, very hard in these early days to predict where that's going to go. But yeah, sure.
Yeah. And then that means then that you probably will have all of these things running all over the place, and surely you won't have enough GPUs to run all of these things, right? So,
and I think it's not just that you won't have enough GPUs. It's just that, you know, okay, so if everyone is running it all the time, the question is really you know, it's how do I scale this thing, right? And right now, you know, the scalability is, you know, is still working, right? Based on, okay, I have a bunch of you know, GPUs in a data center and they are providing this support. But again, it's great if you're in North America, not so great if you're not in North America, okay? And even if you do put data centers everywhere, okay, you're still going to run into the issue of, you know, how close am I to the provider? If I have the ability to run it, you know, on my laptop or on servers that are cheap all over the world, that's a win.
so what are some of your areas of focus as far as R&D with Neural Magic right now?
So what we're doing right now is actually developing the technology to be able to do sparsification on the upstream. So you know, Downstream is great. You use your curated data set, blah, 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 and you do the work. But we believe that it'll be easier if we just provide. So the beautiful thing about LLMs, right, is that yes, there are a variety of LLMs, but it looks nothing like the computer vision space where everybody had their own little model. Here, in terms of foundation models, there's a certain set of things.
There's only a few providers.
Right, and it somehow looks like this is what's going to be true just because of the cost, right? So by being able to provide, right, a sparsified version of these upstream models, right, now you do whatever you want. You run it as is, or you further kind of transfer learn onto it, whatever you want to do, right? So this is where we're aiming. This is one thing that we're aiming in terms of our research. The other direction is to make things much faster. So we are continuously busy. It might not seem like it, but the reason that A100s are so fast is because NVIDIA spent an enormous amount of time fine-tuning the actual software that's running on this thing, right? This is a game that's true for the GPUs, and it's also true for the CPUs. And so we have to continuously be in that business of making the execution faster, right? And that's the other thing that we're doing. And for us, right, it's about sparsity and quantization and utilizing the operations that are available on CPUs. Yeah.
So in terms of speed and making things faster, so what is the main metric that you guys are looking for? Is it like time to first token or
So there are two parts here. There's the prefill part and there's the decoding part, and different applications require different things. So I think to say, oh, it's like this, or oh, it's like that, is a little bit difficult because it depends what your application is, right? I think the interesting thing, right, think of what the benefits of a CPU are. Okay, so the main thing that is problematic for GPUs is that they have a memory limitation. So if you are running, an LLM and decoding on it, right? I mean, you have to keep, in order to utilize the GPU, you need a high batch size, right? And in order to have a high batch size, you need two things. First of all, you need a lot of customers that are running. So if you don't have that, you can't really utilize it, right? And the other thing is, to get a high batch size, you need to have a lot of KV caches around, right? And so that kind of constrains your memory, okay? The beautiful thing about CPUs is that they don't have this constraint. So you can keep a lot of caching. So for example, if you take a typical thing that happens right now, okay, as far as I know, this is how it works, right? Is that if you're let's say accessing OpenAI or one of those providers, right? You are continuously sending your whole context over, and they're recomputing and recomputing and recomputing. Okay, if you could keep the KV caches associated with a certain conversation around, right, in memory, that would save you a lot, right? So this is easy to do on the CPU, right? You can keep it. So that's an example of where the abundance of memory that is available on CPU plays in your favor, even in the cloud. Okay.
Right.
So we are headed in those directions. You asked me where our research is going. We are looking to make the whole process, right? Not just the individual token, right? Did I process that token? But the whole experience, right, of me communicating with an LLM over a conversation over time to make that whole thing efficient. And that involves not just, oh, how fast did I respond to a certain token, but the whole conversation, how much compute and how much delay and how much data did I need to move and how much did I need to save to make that work. So that's where our research is going.
So correct me if I'm wrong here, Nir, but the impression I get is that as far as inference and deployment, there's a big community of people and researchers focused on squeezing more and more out of GPUs. And then there's few folks that are working on CPUs. And this community of people trying to squeeze more and more out of GPUs is much larger than your community. Is that correct?
Yes, that's correct.
I
think it's true.
Yeah, and then which means that there is actually an opportunity for you folks if you prove this out, right? So, but so what do you think it would take for people to finally get that aha moment? Hey, maybe we should look here instead of here.
So I think, I think it's, again, I think it's application dependent. I don't think we're going to beat GPUs on all applications, but there are a lot of cases, right, where people can get away with a CPU and save a lot of money. And for example, right, if you don't have an arrival rate that will support a batch 128 execution, right, or you want a very large context that requires a lot of memory to keep your KV cache. In those cases, the CPU is your natural companion, right? Whereas in the case where you have massive amount of requests per second and you have very short requests, then the GPU is your best companion. So I think there's going to be a piece of the market, right, where a CPU makes more sense. And so if you go to the cloud and you decide how to set up your inference setup, right, it may be that, for you, right, if you're, let's say that your batch size is 8, okay, that's what you can, okay, then you're not going to utilize a GPU. If you take a GPU and to do that, you're not going to ever be able to utilize it fully. So might as well take a CPU and pay less. That's kind of the idea.
Yeah. It seems like that the endpoint providers and cloud providers will need to be good at both, actually, right? So,
I think so, and I think you can also see, you can see this. I mean, there is an abundance of CPU capability in the cloud. I know that everybody has, everybody's adding GPU resources, and this is great, right? And by the way, and I'm not saying that sparsity can't help GPUs, right? I'm just saying that in the cloud on CPUs, there is still an abundance of capability that people can use to get really good performance and for less.
yeah. And also, I think next year, one of the things that might distract away from CPUs is the fact that the AMD GPUs are becoming much more viable for inference. So people might focus first on let's do everything on AMD before we even look over here, right?
I don't know what the pricing of the AMD GPUs is, but yeah, sure.
Yeah.
Are they priced differently from I'm asking you, I don't know.
Oh, I think maybe they're priced less, but more importantly is they're available, right?
I see.
So,
Okay, cool.
but then as we've been discussing, actually CPUs are widely available. If people only knew that they could do inference on CPUs, right?
Absolutely. Yes.
Yeah. And let's see. So in closing, so what about multimodal? No interest at this point?
No, absolutely. I think there's a new Mistral out today that is multimodal. Yeah.
Yeah, and most of the things we talked about would transfer over there.
These are all things, these are all things that are on our agenda. Absolutely.
But it just seems like that enterprises are right now mainly focused on LLMs because obviously the use cases seem to be natural there. Right?
Yeah, I think, again, for us, I'm not sure, again, that at the level that we approach the problem, I'm not sure how much of a difference there actually will be, right? But I agree, as things transition there, right, it will change a little bit the balance of what needs to be done, both in terms of what we'll have to clearly have to change things in our runtime to accommodate this. But but we have not done that yet. I'm agreeing with that.
And with that, thank you, Nir.
Thank you, Ben.